Okay, so in this video I'm just going to continue with the 9 ASP focus questions. There are quite a lot of these, so this is taking a lot longer than my other ones. So in this we're continuing on with bimetallic strips expansion, and we'll move over to pressure and stuff later, the gas laws perhaps. Uneven expansion of bimetallic strips are used in, so this is when one strip will bend more than the other, so that can create a contact with the circuit, or it can break contact with the circuit when it moves away or towards it. So the idea here is this is going to be used in a thermostat, part of a circuit. When the temperature increases, the metal will bend, and then it will touch something to turn the AC on or something to turn the heater off, for example. That's called a thermostat, to do with temperature. The figure below shows a bimetallic strip. The coefficient of thermal expansion of the top is less than the one at the bottom, so more. Coefficient of thermal expansion. This means expands. How it expands? Expand. It is less than the bottom. So this will simply expand less. Expand less. This will expand more. So you kind of get to see what's going to happen then. If this is going to expand more, it will bend towards this one because it's getting bigger and they're stuck together. So it will be bending, bending, bending upwards. So bend upwards. So that's all it's asking. So this question is repeated, so I'm not going to do it. This is in the previous one. We are supposed to know which ones has the bigger coefficient of expansion, and I believe it is aluminium. I did check it, and it was aluminium, so luckily that was correct. And so because of this, this will expand more than copper, and it will bend towards the copper side. So that's all we're going to see. So I can continue on to the next question. Let's have a look. When the gas experiences an isothermal process, isothermal, so there's the clue in the word. Isothermal, thermal means temperature. This means temperature. So there'll be no change in temperature. Iso means stays the same. It doesn't change. So isothermal is same temperature. Isobaric would mean same pressure. Isovolumetric, same volume. I hope you get the idea. And adiabatic is constant heat. Okay, so this is a graph. Which thermal process does this graph represent? Graphs are very important. We definitely need to look at graphs. So if you see something that's going up in a straight line, and look, my pressure is increasing, I can see that. But look, my volume didn't change. This is my volume. It's supposed to increase, but no, the volume is constant. The volume never changed. This is isovolumetric. Over here, my volume is increasing, but my pressure is not. My pressure stays the same. So my volume is increasing, but the pressure stays the same. So that is the same pressure, isobaric, because bar is the unit for pressure. It's one of the units that we can use for pressure, atmospheric pressure, and so on. Okay. What certain quantity of an ideal gas undergoes an adiabatic expansion? Adiabatic expansion is basically constant heat. So gas does no work. No heat is gained nor lost. This is true. Constant heat. I didn't lose heat. I didn't gain heat. Temperature doesn't change. That's not true. And the pressure must increase. It's not true. Adiabatic is to do with heat. Okay. So for the PV graph here, this one is what's happening here? The volume is increasing, but the pressure is not increasing. You can see that the pressure didn't change. Pressure stayed the same. It stayed constant all the way. There's nothing increasing. So this is going to simply be isobaric. Isobaric. If you need to remember the formula for it, I have a video on this, the thermal processes. That just simply becomes Q minus W. And I think it's even on the formula sheet as well. So you don't need to memorize it. Isovolumetric for this one, I can clearly see that right here because the volume didn't change, but the pressure did. So why am I doing that? I can do this. Isovolumetric. And for isovolumetric, the change in energy is simply the heat. And over here, this. Okay, so we have actually two things here. This is isothermal. This is adiabatic. Adiabatic is actually stronger. Adiabatic, actually no, it's not the same. This because adiabatic is much stronger. These two look kind of similar. Adiabatic will come down more like that. Adiabatic has a stronger decrease. So actually this one, I would say both of them would be isothermal. Isothermal. I'd say that, yeah. Isothermal. So if it's isothermal, then there's no temperature increase. So there is no work done, no energy there. The last one over here, there we go, that's adiabatic. So you can see this here is a bigger, steeper increase. Adiabatic has a steeper increase. Adiabatic. And the energy is simply the work done, negative work done. Amazing. Okay. Looking at the next one, moving on to the electromagnetic spectrum. So we need to know which one's which and the correct arrangement of them. So I did this and I showed a little video, a song to my students and get you to figure it out and the different ones. And that is a very annoying song, but it helps. On the left hand side, I'm going to put my highest wavelength. That means I will have the lowest frequency and maybe the lowest energy. Of course, on the right hand side, it'll be the opposite. It'll be the lowest wavelength, highest frequency and highest energy. Starting from the first one, we call them radio waves, then microwaves, infrared, radiation, visible light, ultraviolet, X-rays, and then gamma rays. That's kind of how the song goes, and it helps me remember. So, longest wavelength to shortest wavelength. Which one is the correct one? Ultraviolet has the shortest wavelength. That's over here, and that's shorter than visible light. So that's wrong already. Ultraviolet, then infrared. Well, that's here to infrared. Again, that's wrong because that's short. I want from longest to shortest, so that's wrong. Visible light is here, followed by infrared. Again, wrong way. This is bigger wavelength than this. That's not good. Infrared, okay. Then to visible, okay. And then to ultraviolet, correct. Big wavelength to small wavelength. This is correct. So knowing the order of the spectrum definitely helps. And just a fun fact, inside this one we have Roy G. Biv. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. And they follow the same idea, bigger wavelength and so on. That will actually be more important in grade 10. You'll deal with that later. Compare the wavelength of energy, gamma, microwave. Okay, gamma, microwave. Very nice. So let's figure it out. So we're saying a gamma ray photon, a microwave photon has. So the microwave, which is over here, look at this, microwave's here. Gamma's over here. So microphones, this is on the left. This has a bigger wavelength, smaller frequency, smaller energy. So microwave has a bigger, what happened there? Bigger wavelength, smaller frequency, smaller energy. So shorter wavelength is wrong. Microwave photon, shorter wavelength is wrong. Big wavelength, yes. Less energy, yes. Long wavelength and more energy, wrong. So C is the answer. I see that they've written B over here. I guess that's another mistake in the answer key. Nope, it is actually C. It has a longer wavelength and a smaller energy. So, very good. Next, so this is, you have to identify the missing parts. So let's do that then. Radio waves, microwaves, infrared, radiation, visible light, ultraviolet, X-rays, gamma rays. Very good. So that's the idea. Easy. In a vacuum, all electric waves are in a vacuum, like in space, there is nothing blocking them from moving. They all will have the same speed. Which of the electromagnetic waves travel fastest in a vacuum? Trick question. They all have the same speed. Nice and tricky. Alright, so next we're going to move on to ray diagrams. So that is going on to light and stuff. So let's do the ray diagrams questions. This is a good question. So in this case, you need to find alpha and beta. Well, this is the law of reflection. Incident ray is equal to the reflected ray. And this is the normal. All angles are taken from the normal. If that's 26, that's 26. Already, I know this is 26 and 26. C and D are wrong. Then, if I know this one here, I need to figure out a way over here. There's a couple of ways you can do it, to be honest. You can turn this into a right-angled triangle if you like. You can do 180, so minus 90, minus 26, and you'll get this angle. And this angle will be equal to this angle. We can go ahead and do that. Let's try that one, shall we? So I'm going to do 180, that's the whole triangle, minus 90, which is this one, minus 26, which is this one. And if you were to do that, you should get, hopefully, 64, which means this is the answer. You'd know that because A and B would not be the same, it would be different. Let's check to make sure this is correct. Let's check our answer. If you wanted to, I could also find out this angle and do the same thing, find out this angle, and then I can go that way. This is the good thing about math. There's more than one way to solve it. So if this is a 90-degree angle here, or even 180 minus all of that. But if it's a 90-degree angle right here, I will do 90 minus 26. 90 minus 26 happens to be 64. And this one will be 180 minus 64 minus also this 90 over here. So 180 minus 64 minus 90, same thing. Let's do it. That becomes 26. I like it. This is 26. If that's 26, this one here will be 64. Same way. And that's 64, that's 64. So we've solved it. There is a third way. If you're really good with math, you can kind of see that this becomes like a little Z. One of the theorems, interior angle theorem or something. This angle is the same as this angle, basically, if you make this little Z. So if you knew that this was going to be 26, then I know this one's also 26. If that's 26, that becomes 64. That's another way. So there you go. You've got 3 ways to do it. That's 3 ways to get the answer. It's really good. Good fun. All right. A ray strikes a mirror as shown. What is the angle which is reflected from the mirror? It is the same angle. So the angle will be the same angle. It doesn't say the angle, so it will say same angle. Fine. You can I and R. Okay. Which of the following is a statement not a characteristic of a plane mirror, not a characteristic of the plane mirror. So that means we're going to say, well, a plane mirror is like this. If you're standing in front of the mirror, you will see yourself in the mirror. You will become a virtual image in the mirror. You can see yourself. So it's not a real image. No, this is the one that's not a calculate. This is actually the answer. This is not a characteristic. It is +1. It is the same magnification. You look like the same size in the mirror. It will be upright because you can see your face clearly. And it will be reversed. So you're looking at a mirror image of yourself. So it'll be a reversed image. Which of the following describes the image formation by a plane mirror? We just discussed that. It'll be a virtual image, the same size, and it'll be reversed. So this is, I can say virtual behind the mirror. I see in front of the mirror is wrong. Real, wrong, and wrong. That's why I didn't even look at them two. I looked at this one first because it was the longest. Usually the longest statement ends up being the right one. So virtual image is formed behind the mirror. Virtual image formed in front is not true because it is behind the mirror, behind. Okay, this is in front. You're standing in front. Okay, which describes the mirror, the image formed by a plane mirror. Just said it is virtual. It is the same size, and it will not be inverted. It'll be upright. So that's wrong. Real is wrong. This is correct. Real upright. Real is wrong. So an object at a distance 0.5 meters in front. What is the distance between the object and image? Okay, so basically here, between here to here is 0.5. What is the total distance? Well, if it's a mirror image, this should also be, this is too close. It should also be 0.5. The total distance will be 1 meter. Simple as that. So you just add them. So you just times it by 2, just add it. 0.5 plus 0.5 gives you 1 meter. Okay. Let's see what else we got. 60 centimeters in front of the plane mirror. What is the image distance? So it didn't say the distance from the object. It just said the image distance. So that is going to be also 60 centimeters. Now, if you remember, if you have a mirror and you have an object in front and behind, this side's positive, this side's negative. So technically, if this is 60, this should be minus 60. So I need to add a little minus in here. Next, what is the distance between the object and the image? Then that's basically the total thing, right? That's 60 plus 60, which is 120. 60 and 60. You don't need to include the minus for this one. It's the total distance. Distance is a scalar. Distance, 60 plus 60, 120 meters or centimeters, I guess, right? It's centimeters. Okay. What type of image is this one? So this is, as you can see, that the kind of bending like this. This is going to be as a mirror. So if I draw the whole mirror out, it will look something like that. This looks like a concave mirror. So I'll pick a concave. A lens, it would have passed through it and bending after passing through. But this reflected, so it became a mirror. For example, that's a concave. Convex would be like this. That would be a convex when the light hits. It would be convex. A concave mirror has a radius curvature of this. How close to the mirror should an object be placed so the rays travel parallel to each other after reflection? So the idea for this one is you can actually draw this out. This is actually going to get very long now. You can draw this out. If I had my mirror over here, it's a concave mirror like this. I have my focal point. I have my radius here. it's the center or the radius, we can say. And what am I doing? The radius is 60 centimeters, 60 cm. How close should the mirror be so the rays travel parallel to each other after reflection? So basically you will not be able to see the image. This is going to be exactly the point. It will be halfway, this position here. And that means you would have to put it right here, which is maybe 30 centimeters on the focal point. So that'll be 30 centimeters. Now actually I'm going to explain all of this. I should make another video because it will take some time. So I'm going to pause the video now and I'll continue to the next one. Thank you.